Welcome, class, to the next topic in our unit on sequences. And today it's about, it starts off anyways with interest, two different types of interest, and not the interest we use when we're talking about our favorite things, but interest, mostly we talk about it with money, how much money grows by. And our initial learning target here is I can calculate simple and compound interest. It kind of morphs into something else soon. And the rest of this video will talk about growth and decay in general, not just about money, but we're going to start with money. And we're going to break this up into two distinct equations. There's going to be one called simple interest, and it's essentially finding a percent of something. It really is simple. It's there for a reason. It is super simple. And then there's compound interest, which is much more realistic. I can't spell. And because it's more realistic, of course, it has a slightly more annoying equation. Simple interest is this. You say interest equals PRT. So I have to know what those letters mean. So I means interest. P stands for principal. And it's the principal, like the principal of a school. Then R equals rate. And you put it as a decimal. So if I said 5%, you would put 0.05. And then T equals time. So that's going to be really easy to calculate. You just plug those three things in and you get your interest. Compound interest works a little differently, and it's because, let's say you go to the bank, you put in $500 on January 1st. A year later, it has grown whatever percent the bank gives you, let's say 10%. So your $500 has gained $50 because that's 10% of the 500. If it was simple interest, that's all that's figuring out is it grew $50. So the interest would be $50. And maybe the bank, if it only worked with simple interest, would put that $50 in an envelope and send it to you. And then you still have $500 in your account. Well, banks don't do that. They just put the money back into your account. So if I wanted to figure out after 10 years how much I would have, if I forgot about this $500, well, the first year it would grow 10%, which is another $50. But then the next year, I have $550 in my account. And instead of growing just $50, I would grow $55. So now I have $605. And then it keeps going after that. So all this money that builds gets put back into the account, and that's what compound interest figures out. And that's a lot more complicated because every year it's a different amount. So we're going to write an equation that adjusts for that. And it looks like this. So it start with A, which is the amount after whatever time it takes, equals the principal again, times 1 plus the rate divided by how many times it's compounded through the year to the power of n times t. So t again is time. So this equation gets a little simpler in just a minute, but let's explain all these things. So A equals amount. So it's, if you put $500 in, you want to know how much it'll be after 5 years. A is that number, that final amount. P again is principal, what you start with. I don't know if I explained that in the last one what principal meant, but principal is what you start with. Let's see. R equals rate. Again, it's the same deal as a decimal. T equals time. Same deal there. So nothing new except for this n. So this n is number of times compounded per year. So you know how I was saying that at the end of a year, that $50 gets added in. Well, sometimes a bank will compound every month, or maybe even every day. And so that allows it to grow just a little bit faster because we're adding in money at the end of that month, a little bit of money at the end of the month, and then all of a sudden the rest of the year there's that much more to get the percentage of. I know it's a little bit confusing, but you generally want to compound as much as you can. What does it say? Number of times compounder a year? Compounded. I think that's supposed to be a D. Number of times compounded per year. Now, if every problem we do from here on out says compounded annually, think about that. That means it's only once per year. Let me use a different color here. That would mean n equals 1 is compounded annually. Oops. If it's compounded annually, n is 1, that means this is 1, and this is 1. And 1s in those places don't change the r or the t. So a much simpler way to write this, but you just have to remember that this is for compounded annually, is this. So you have a lot less to worry about. There's no fraction in the middle. It's just one exponent instead of being multiplied by two things. So if you want to use compounded annually, which is what most of our examples will be, you're going to use that formula actually. Alright, we're going to do a really simple problem that just shows how simple interest works. It says Kyra has been babysitting since 6th grade. She saved $1,000 and wants to open an account at the bank so she will earn interest on her savings. Simple bank pays simple interest at a rate of 10%. How much money will Kyra have after 1 and 5 years? Alright, so we write our simple interest formula, which is the interest equals PRT. Interest equals principal would be what she starts with, that's $1,000. The rate says it pays 10%. Now remember, I don't plug in 10, you plug in 0.1, put it in parentheses. And then time, we have two different situations. We have 1 year and we have 5 years. So let's do the 1 year first. So this is really easy. 1,000 times 0.1 is just 10. Scratch that, 100. So her interest after 1 year will be $100. 10% is a pretty good rate. I don't think most banks will pay that for a savings account. So she has $100 more. Doesn't mean she has $100 after 1 year. That would be a terrible bank. It means she has 100 extra on top of her 1,000. So for 1 year, she'll wind up with $1,100. But now we need 5 years. So after 5 years, we just change this number to a 5, and it becomes 500. I'm being lazy. You shouldn't be lazy. I'm crossing out my original problem. So if it was 5 years, $500 would get added onto 1,000, and she'd have 1,500. So even though it was a good percentage, she's not benefiting from all that money that's added in every year to be also counted. Alright, so here's an example of compounded interest. It says Jack has $500 to invest. The bank offers an interest rate of 6% compounded annually. So there you go again, it's annually, so we can use that simpler equation. How much money will Jack have after 1, 2, 5, 10 years? So we need that other equation, A equals P times 1 plus the rate to the power of T. So notice we don't need the n's in there because it's not being compounded more than once a year. And then we fill in. This time, my final answer won't just be the interest. It will be the final amount. So principal is 500. 1 plus the rate. So this is 1 plus 6%, which is 0.06, to the t, and we're going to start with our first one, which is to the 1 power, which as we know, it doesn't change anything. Now this should start to look really familiar. You might be thinking, hey, this looks like the geometric pattern that we did last time. And you would be right. So this is 500 times 1.06. And get a calculator and we get a nice clean $530. So in this formula, what the formula will do is we'll take that $530 and add it in so it can use it for the second year. But we don't have to do that every time. We can just plug a 2 in for our exponent to get our next number. So I'm going to do this one more time by hand, but then show you a way nicer way of doing this. So again, I plug in, most of the things are going to be the same, 501 plus 0.06, but now it's to the second power. We get a calculator and we get 561.8, so $561.80. Again, if we just, so you can see that the first time it added $30, and the second year we added $31.80. Not a whole lot more, but we didn't say compound interest was magic. It just took that extra $30 and got the interest from that too. So 6%, and actually we can kind of test this out. 6% of 30 is exactly $1.80. So that's kind of cool. It shows that the formula was doing its job. It took that extra $30 that we gained that first year, stuck it into that amount, and on the second year you got an extra $1.80 because of that extra $30. And that builds up over time. Obviously $500, not a ton of money. If you had, let's say, thousands and thousands of dollars in, you had a slightly better interest rate and you waited many years, it's going to make a huge difference. Alright, we're going to do one last thing here, and we decided, so math people long ago decided that, hey, this works not just for money, this works for anything that grows or decreases in this manner, like those geometric patterns do. So they developed a formula that didn't have to do with money. So in this case, we're not going to use letters that represent things to do with money. We're just going to use more generic numbers, but you'll see that the equation is essentially identical. So we'll say growth looks like this. So we'll start with a y, the classic y, equals a, and we'll call that our initial amount of, could be money, it could be people. And then we notice that's really familiar so far. 1 plus the rate, so that's going to show growth when we're adding the rate every time to the power of t. So time is still involved. But actually, let me get rid of t, because again, even though it's time always, I'm going to write an x. Since we used y, we're going to use y and x, because these are always a function of time. So this could also be written like this. A function of x equals a 1 plus r to the x. So those two things are the same thing. Decay, I'm only going to change one little thing, and that would be this part, 1 minus r to the x power. So no, they're really the same exact thing. Instead of principal, we use just the letter a. Instead of an amount of money at the end, we use the letter y. Instead of time, we use x, and rate's always rate. Okay, I think this is going to be our last problem. I had 2 planned, but I don't want to go too long. So this is the population of the country Oz was 600,000 in the year 2010. The population is expected to grow by a factor of 5% annually. The annual food supply of Oz is currently sufficient for a population of 700,000 people and is increasing at a rate which will supply food for an additional 10,000 people per year. So we're kind of figuring out if the population will outstrip the food supply, which is something that many people do get concerned with in real, non-fantastical places like Oz, like New York, or a certain country whose population is growing but their food supply can't hold up. So we're going to try to figure this out. There are two things happening. One of them is that the population is growing annually by a percentage. That's a geometric pattern. We're going to need a growth formula. So we're going to start with that same growth formula you just wrote. Y equals A times 1 plus the rate to the power of x. And we're going to try to fill in what we know here. So we don't know what y is. Y is that final amount of, in this case, people. And A is 600,000. That's how many people they had in 2010. And then the rate is 5%, so we're going to say 1 plus 0.05 to the power of x. We can clean this up just a teeny bit. 600,000 times 1.05. I'm just adding those things to the x power. So we're going to get a calculator out to do this in just a second. But let's first come up with the equation for the other thing that's happening. It says the annual food supply of Oz is currently sufficient for 700,000 people, and it's increasing 10,000 per year. Well, it goes up 10,000 per year every year. That's not a growth or decay. It is growing, but it's not growing exponentially. It's not growing geometrically. It's growing arithmetically or linearly. It's going up the same amount every year. So that's a much simpler formula that has to do with slopes and y-intercepts, or at least starting positions and rates of change. So we'd say y equals, and we want, this is where m normally goes. This m is slope or rate of change. Well, if it goes up 10,000 per year, that's the rate of change, 10,000. X would be years, just like it is in the other equation. Plus, you start off by having enough food for 700,000 people. So there's that equation. It's really gigantic. Lots of zeros. So I didn't have to do much work to get that one. I just had to know what is the rate of change, what is the initial value or the starting position or the y-intercept. So this doesn't really help us, these two equations, just staring at them. I don't really know how long they can last on this situation. So we're going to use our calculator to help us out. Alright, we'll try to make this quick, but we're going to put some equations in our calculator. So if you look back up at the two equations we wrote, we're going to enter them in the calculator. And to do that, you hit the y equals button first. That's the red one right here. And then we'll put the linear one in first. We'll just put 10,000 x, and this is the variable button right here. X is the one we want. Plus, and then 700,000. Alright. Just so we can get a sense, we're going to graph it. We don't need to do it. We could put both in and then hit graph, but I just want you to see what it looks like. If you hit the graph button, everyone's going to be a little bit different. Mine takes a little bit of time, or it doesn't show. I don't think it'll show it at all because I haven't adjusted my window. So if your window only goes up to 10 and this thing starts at 700,000, we're not in the right place. So we need to adjust our window. So notice this window button here. Right here you can see it starts at -10 and ends at 10 for the x values. For the y values, it does the same thing. So it's like a 10 by 10 grid. That is not what we want. Now I could enter in values if I wanted to. I could make sure, I could make say that y starts at 700,000 and then goes up to like 800,000. But instead, if you hit the zoom button, it could do a lot of the work for you. So if you hit zoom, and all these things have different abilities, but we're going to do zoom fit. And I think it's somewhere just below Yeah, right there, number 10. So you can hit 0, or if you just hit enter when you're on that. Zoom fit, and there you go. It kind of tries to put the main part of the graph in the middle of the screen. So here's the y-intercept. Here's your line. It doesn't tell us much yet without the other equation. So we're going to go back to y equals. And we're going to go down to y2 and enter in 600,000 parentheses 1.05, and then to the power of x. So we use the caret button that raises the power, and we put our variable in. And again, I hit graph. I don't know if it's going to be perfect. There's the other one. I'm not seeing it right now. It is still working though. There we go. So it looks like a line, but it is not a line actually. I'm going to hit zoom fit one more time just to see if it changes anything. Again, remember you can just hit 0. It does have to redraw everything and sometimes can be a little bit slow. So it's going to make it look a little more curved, which is nice. Alright, so we can see that after a certain amount of time, this population growth is going to go past the amount of food. So here's like our food supply. It increases, but not as fast as the population will increase. So this is like a dangerous time for these people of Oz, because all of a sudden they're running out of food. So we want to see where that intersection is. So your calculator can do that really easily. If you hit this little calculate button right here, if you hit second calculate, we can see the intersect. So we're going to hit 5. And then it wants you to say, it says first curve, it just means the first equation. So we'll say, yep, that's the first one. Yep, that's the second one. And then it wants you to guess for some reason, but we're not going to guess. We're just going to hit enter. It'll find it for us right there at x equals 4.412. Now remember what x values represent? They represented years. Y was the number of people, either people in the world or people that we could supply food to. So in 4.41 years, so a little less than a year and or 4.5 years, they will have exactly the amount of food they need, and beyond that, they will have not enough food. So your calculator is super powerful. You can get that exact value, that exact moment in time where your food supply and your number of people is the same. Alright, I'm going to end it here. We're going to practice this more. We're going to practice it with a calculator more in class. And I'll see you when I see you.